Hi there, in this video we'll be talking about the absolute value function. Now I know you're already familiar with the absolute value in some way, but maybe you've never thought of it as a function or as its graph. So this will be a nice example for us to see something that's not a line. It's a little more sophisticated than a line, but we'll be able to graph it rather easily and understand transformations. So take a moment and just compute these things. I'm giving you 4 absolute value problems. If you think they're easy, you're right. Absolute value of 3 is 3. Absolute value of negative 45 is 45. Absolute value of 7.19 is 7.19. Absolute value of negative 1/3 is 1/3. So I think most of you are very comfortable with how to do absolute value. But what is it actually equal to? Right, you can say, oh, it's the thing that turns negatives into positives, but that doesn't really feel like a definition. The way you should think about what absolute value really is to think about a number line. Here's the number 3.2 on the number line. When I compute the absolute value of 3.2, what I'm measuring is how far away from 0 is it on the number line. And that distance would be 3.2. But if I have a negative number like negative 2, I go in the other direction, but that distance is 2. So the way you should think about what absolute value really is as a distance. So here's what the book says in terms of an essential understanding. The absolute value of x is the distance from 0 of x. And if we start doing this with functions, the absolute value of f of x gives the distance from y equals 0, which we can think of as a line, to f of x. That second part's a little tough to interpret. We may make more sense of it later on. So let's think of the absolute value as a parent function. Let's really understand the absolute value as a function. F of x equals the absolute value of x. And we know we can approach functions a few different ways. So one way of understanding a function is through a table of values. And I would encourage you to fill in this table with the integers from negative 3 through 3. The negatives get turned into positives, 0 stays the same, the positives stay the same. This is one way of understanding what the absolute value function does. We're listing specific input and output. Another way is in terms of a formula. And this is using something called piecewise notation that you will probably learn more about in pre-calc. But the idea is that we're explaining what this function does by breaking it into cases. What is the absolute value? Well, we're really saying two things. We're saying if we're looking at a number that's at least 0, then the absolute value of x is just x. Think of any positive number. The absolute value of that positive number is the same as the number we started with. But if we're picking a negative number, then it's actually the opposite. This means the opposite of x, not negative x. So the idea is if x equals negative 5, the absolute value of x is the absolute value of negative 5, which is the opposite of x. So it's a little tricky here. This looks like a negative number, but if x is negative, this is positive. So this is a very rigid, abstract way of thinking about absolute value in terms of this formula that breaks into two cases. Maybe the easiest way to understand this is to think about the graph. So I had that table of values. Let's plot those. I had a point where x was negative 3 and y was 3. One where x was negative 2 and y was 2. Negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3. I'm not labeling all of them. And if we play connect the dots, it'll be like this. So the graph here is V-shaped. It's a graph that has a corner, which is somewhat unusual. But this is the pattern that explains things. And what we'll notice in terms of linking it with this formula, we'll see that sometimes the graph is like y equals x. The line y equals x goes like this. And sometimes it's like y equals negative x, which goes like this. And that ties to this formula. This is sort of an abstract way of saying I'm dealing with a function that sometimes looks like the graph of y equals x and sometimes looks like the graph of y equals negative x. And this graph you should just know. You should know right away, oh, when I graph the absolute value function, I get this V-shaped graph. So the graph is V-shaped. It's symmetric about a vertical line called the axis of symmetry. So here it's the y-axis, but just generally speaking, the vertical line that runs through the middle of V is called an axis of symmetry, and the corner point is called a vertex. Even if we had a different V-shaped graph, we could still talk about its vertex and its axis of symmetry. But this graph I want you to know. If I ask you about the graph of absolute value of x, you should be able to come up with this relatively quickly. And once we're familiar with that parent function, we can think about related functions, right? We now know these transformation rules, and they're still very new, but we can start playing around with them. What if we did something like y equals the absolute value of x minus 4? So I'll first make sense of this in terms of a table. So if I plug in 2, here I would have negative 2. Absolute value of negative 2 minus 4, which is 2 minus 4, which is negative 2. Absolute value of negative 1 minus 4 is 1 minus 4, which is negative 3. These are just computations. I'm doing them quickly, but I'm not doing anything all that exotic. And we could graph this by plotting those points. And you can mostly watch this. I'm doing it really quickly. Maybe it's better for you to just think about this. I have a point where x is negative 2 and y is negative 2. I have a point where x is negative 1 and y is negative 3. I have a point where x is 0 and y is negative 4. I have a point where x is 1 and y is negative 3. I have a point where x is 2 and y is negative 2. And then we'll just sort of hope that we can connect these in the most plausible way. So there is our graph of y equals the absolute value of x minus 4. But what we might notice is it looks just like the graph of y equals the absolute value of x, but shifted down. These two graphs are exactly the same size, shape, and orientation. I've just pulled the black one down to turn it into the red one. And that should remind us of how these transformation rules work. We know in general, if I just subtract 4 at the end of the formula, that shifts the graph down 4 units. So that general rule is in play with this specific function. So here I'm just summarizing the rules we already knew about transformations in the very specific context of the absolute value. So hey, if I add on the outside, that translates the graph up. If I subtract on the outside, it translates it down. If I subtract on the inside, it shifts it to the right. If I add on the inside, that shifts it to the left. All of these we saw before. If I multiply by a number bigger than 1, it does a vertical stretch. If I multiply by a positive number smaller than 1, it does a vertical compression. Putting a negative outside reflects across the x-axis, which turns it upside down. Putting it on the inside reflects across the y-axis, but you'll notice this graph is already symmetric to the y-axis. If I flip left and right, it looks the same. So really what happens is this is the same as the original absolute value. And that hopefully makes sense. A negative in the absolute value just turns into a positive anyway. So all of this you've seen before, but it's good to keep reinforcing. So let's look at an example. Let's use transformations to graph this function. So just watch me do this one and you'll have a couple to try. So the idea is that lurking within this is this parent graph of y equals the absolute value of x. And we've done two changes. When I add inside, that's going to shift it 2 units to the left. And then when I add outside, that's going to shift it 3 units up. I'd recommend doing this in 2 steps. After you've practiced a lot, you can probably do it all at once. So what I would recommend is just start with your basic V-graph. And as far as I'm concerned, 3 specific points and the overall picture will be enough. So here's my absolute value graph. 1, 1 is on there, 0, 0 is on there, -1, -1 is on there. So now, what would that look like if I shifted it 2 units to the left? So I'm going to draw another grid here. And this time I will put some tick marks on it. So what I recommend is shift the individual points, then redraw the graph. We had a point at 1, 1. Where will that point go if we shift 2 units to the left? The point that was at 1, 1 will go to -1, 1. We had a point at the origin. Where does the origin go if I shift 2 units to the left? It goes to this point, -2, 0. We had a point at -1, -1. Where does that go if I shift 2 units to the left? It goes to -3, 1. And then we'll just reconnect into our V-shaped graph. This blue graph is exactly the same size and shape as the red one, but we've moved it over. Now we're going to move it up. All right, so I guess what I could actually do here is I could try just making a copy of this. Oops. So now I could say, well, what happens to that blue graph if I shift it up 3 units? And as before, we can just pay attention to where individual points go. I had a point here at -1, 1. If I go up 3 units, 1, 2, 3, that winds up at, let's do this in pink, that winds up at -1, 4. I had a point at -2, 0. If that goes up 1, 2, 3 units, it winds up at -2, 3. If I had a point at -3, 1, if that goes up 3 units, we have a point at -3, 4. And our final graph, as we would expect, is V-shaped. This pink one is the final answer. That's the result of taking the original graph that had its vertex at 0, 0, and we shifted it 2 units left and 3 units up. So it makes sense that the vertex is now at negative 2, 3. We shifted the whole graph 2 to the left and 3 up, so that's where the vertex wound up. But the size and shape are the same. So take a moment and try these. Try graphing y equals the absolute value of x minus 2 plus 1, and try graphing y equals 1/2 of the absolute value of x. If you think you can do this all at once rather than in steps, give that a try. So hit pause and actually try these. Okay, so here what we might notice is that this is like y equals the absolute value of x, but we shift 2 units right and 1 unit up. So if you're feeling rather ambitious, you can try doing this all at once. Figure out where the vertex is. For ordinary absolute value, my vertex would be at the origin, but I've shifted 2 to the right and 1 up. So here, this point at 2, 1 will be our vertex. But then the rest of this is the exact size and shape of the normal absolute value graph. So in the normal absolute value graph, the slopes are 1. I can go 1 over and 1 up. So if I wanted to be specific, there's a point here at 3, 2. Could go 1 over and 1 up again. There's a point here at 4, 3. I could go 1 backwards and 1 up. The point here is at 1, 2. And I could label a lot of these points. I'm not super concerned with specifically labeling every single point. I'm much more concerned with you understanding, oh, hiding within this is the parent function of the absolute value of x, and we know what that looks like. And we understood that we're taking that graph that used to have this corner down here, and we're shifting it over and up. How about this one? This makes it half as tall. So here I will draw the original for reference. So for my original graph of y equals the absolute value of x, some specific points would be 0, 0, 1, 1, 2, 2, over here, negative 1, 1, negative 2, 2. When I multiply by 1/2, I make every point half as tall. So here, 2, 2, when I make that half as tall, I get a point here where the x is still 2, but my y is half as much. Here, I get a new point that's half as tall. The x is still 1, but the y is half as much as it used to be. 0, 0 stays the same. Over here, it's a mirror image. I had a point here where x is negative 1 and y is 1. I'm going to go half as tall. The x coordinate is the same, but the y coordinate is half as much. Over here, same thing. X coordinate is the same, but the y coordinate is half as much. So this point is at negative 1, 1/2. This point is at negative 2, 1. Don't feel like you have to label everything. It's more important to understand overall how is this changing. I'm taking that purple graph and basically I'm squeezing it downward so it's now half as steep. So the red graph is half the absolute value, while the purple graph was the original absolute value. So I'm doing these really quickly, and I'm not expecting you to do it so fast, but I want you to just be able to see that general relationship, regardless of the overall labels. Hopefully you can see that the red graph is like a compressed version of the purple graph. Right? And don't get thrown off by the arrows looking a little bit wider. Right? If I drew my arrow here and my arrow here, then maybe it's a little more obvious that I'm pushing it down. Yeah, it also looks wider, but what we're really doing is we're taking that purple graph and we're compressing it lower. Okay, final page here. is what's called the general form of the absolute value. So the idea is, no matter how much we monkey around with all of those transformations, if we start with absolute value, when we're done, we'll get something with this form. Maybe there's a number on the outside that reflects multiplication, and maybe it's negative, so there's a flip. We're adding or subtracting inside, and we're adding or subtracting on the end. And there's a reason why I have minus here and plus here. But if you see something of this form, you know right away that A is basically measuring the stretch or compression factor. Might be negative, so you have to be careful about that. Here, assuming h and k are positive, we've shifted h to the right and k up. So that would move the vertex. And so whatever h and k are, that's what the vertex is. And x equals h would give us the axis of symmetry because that goes through the vertex. If A is positive, the V opens upward because we haven't flipped it. If A is negative, we multiply by a negative somewhere and the V opens downward. So this is going to take some time and practice. But what I want you to realize is if you understand this general pattern, you can look at any V-shaped graph, and that includes upside down V's and wide V's and steep V's. And you can figure out the formula. So let me show you an example. I could look at this and say, all right, I have a V shape where clearly my vertex is at the point -1, 4. So right off the bat, I know that my formula would be y equals a, which is some number I haven't figured out yet, times x minus -1 plus 4. The coordinates of the vertex just go in as what we're subtracting here and what we're adding here. So it looks like this. And hopefully you'd think, yeah, if the vertex is over here, I shifted 1 to the left and 4 up. Now, we need to figure out A. Because we're opening downwards, we can say that A is definitely negative. And how big it is has to do with slopes. So what we might notice, for example, is that this is the point 2, 3. So if I wanted to find the slope of that side, it's the change in y over the change in x, which would be 1 over -3 or -1/3. By symmetry, the slope over here would be 1/3. So this is less steep. It's less steep by a factor of 1/3. For normal absolute value, the slopes are 1 and -1. Here they're 1/3 and -1/3. So what we're noticing is that we have 1/3 the steepness. So combined, that means that A is -1/3. So for that graph, we can now conclude that we are looking at a graph of y equals -1/3 times the absolute value of x plus 1 plus 4. If you pulled out Desmos or your calculator to graph this, it would look like that. So try it on your own with this one. Figure out where the vertex is, figure out if A is positive or negative, measure slopes to figure out how the steepness has changed. So hit pause and give that a try for a moment or two. All right, I hope you've tried that. So what do we see here? My vertex is at 1, -5. So I've definitely shifted 1 to the right and 5 down. A is going to be positive because we're opening upwards, but its exact value depends on slope. So we might notice here's the point at 1, -5. Here's a point I can clearly see at 5, 3. So my slope is change in y over change in x, which is 8 minus 4, which is 2. So that's pretty easy. You could have gotten that a lot of different ways. So if the slope is 2, it's twice as steep as usual. And it's positive. It's not upside down. So A is going to be equal to 2. The slopes tell you what A is, you just have to check if it's positive or negative. And again, this is a very checkable problem. On a test or quiz, I might put this on the calculator section so that if you can figure this out, I want you to put it in your calculator and say, oh yeah, for sure this is correct because I just graphed it and it looks just like that. All right, so that's the end of